I'd like to convey some things in the next 30 minutes. A number of insights I think it's useful to have when we're thinking about artificial intelligence in its large scale. One of the challenges that conversations about artificial intelligence have is that they tend to be very undifferentiated. And so the goal of my talk is to introduce some differentiations that may be really helpful in framing the conversation that goes on. I cut down an hour-long talk to this 30 minutes, so I'm planning to go fast to get through it in the 30 minutes that I have. I'm going to make the case to you that you can think of AI as coming in three waves of technology. The first wave being handcrafted knowledge and statistical learning, and the third, which we're only just starting to get into, is contextual adaptation. And the claims that I have about these three waves, even though they start in a sort of historic way, they don't end in a historic way. Indeed, just because something is first wave doesn't mean it's old, doesn't mean it's boring. And there's a number of things that we're doing actively at DARPA at the moment in first wave technologies. Second wave is amazingly effective. We see it again and again with face recognition, speech recognition, all of these kinds of things, but it has fundamental limitations, and when we understand limitations, I think that will be helpful for us in framing the safety and control conversation. The third wave, in our view, is just beginning. We're starting to see what's needed, but we don't see it very clearly yet. So we'll charge into looking at these three waves. I'm going to spend most of my time on the second wave, understanding these fundamental limitations by looking at the nature of it, but then moving into the third wave. So let's start with first wave. Bill already referred to it in his introduction. First wave technologies are those technologies where human beings craft the frame of the knowledge. So think about traditional expert systems, for example, or TurboTax that you may have used relatively recently. That's a great example of a first wave technology where human beings have crafted expert quality rules about a complex situation. And what we find with something like TurboTax is that it's very effective for the particular kinds of things that it has to do. I've got a little four-point scale of intelligence here, different dimensions of intelligence. This isn't intended to be absolute, but it gives you a flavor of some of the dimensions of intelligence. So let's take TurboTax. It's got limited ability to perceive. That is, you can say, here's my W-2, and it can make sense of it. It can perceive that, it can pull it in, but you can't say, and here's all the receipts from the last year, and hope that it will be able to figure out what. Limited ability to perceive, but only limited ability. It has no ability to learn. If a new piece of legislation comes out, somebody has to do the coding to reflect that in there. It certainly has no ability to take a whole pattern of learning and do a meta-learning, which I'm calling abstracting. There's no ability to abstract in TurboTax. But it is pretty good at reasoning. And in fact, we find that true of many typical of first wave systems, that we craft the structure of knowledge, and then the computer is able to follow the implications of that knowledge and push reasoning quite a long way, often reaching human levels of reasoning in the particular capability. Chess, for example, machines are able to outperform human beings in being able to reason about how to think about chess. And we've had a lot of success using these kinds of technologies for things like logistics, and being able to bring together information from different sources and make sense of it. One place where it's really hot at the moment is in cybersecurity, software analysis. This is one of my to say, just because something is first wave doesn't mean that it's old and boring. If you look on the right, here's a set of DARPA programs that are active in this first wave of technology. This is a space where human beings craft the structure of the knowledge, and then the specifics are explored by the machine. So you can say, here's how information flows through a program, and then by looking at how information flows through a program, the machine is able to say, I think there's a risk of a buffer overrun here. You freed this pointer, and then somebody used it after it got freed, and that's a potential vulnerability. And things like that. The computer is able to follow the reasoning process. One nice example of this kind of work is in a few weeks' time, we're running a competition between Black Hat and DEF CON out in Las Vegas. It's Cyber Capture the Flag. And here we've got 7 teams, each with a supercomputer. All the supercomputers are all studying each other's code and trying to figure out where's a vulnerability in the other person's code that I can get in and retrieve a particular piece of information from the computer, and where are the vulnerabilities in my code that I can automatically, at machine speed, identify and fix. This is great cutting-edge research, but it is very much the structure of the knowledge is defined by human beings. The specifics then are explored by machines. Now, the challenge with first-wave technologies is that while it's wonderful when you can structure the knowledge that way, it stumbles when you deal with natural data. When you look at the kind of data that we get in the real world, it's very hard to characterize it. Like if you sat down and defined all the characteristics of a cat picture, it would be really hard. There's no way that you could get all the nuances so that you could have a set of rules that ended up saying, yeah, this is a cat and not a Pomeranian or something like that. So second wave technologies, people talk about machine learning. I tend to avoid the phrase machine learning because that sounds like the machine just learns, like you just learn. And actually, one of the things that's not often said but is foundational to what's going on in machine learning is that somebody has spent a lot of time crafting the framework that is able to learn. That is, what's really going on is that engineers have worked hard to create statistical models in great detail, but these statistical models have vast numbers of parameters that when you give them lots of data, those parameters get tuned to particular values so that they're able to accomplish something effectively. So one of the exciting things about these kind of second wave technologies, we see it with, for example, Siri or Google Search or Watson and many others, face recognition on Facebook and so on. They give very good classification and prediction capabilities. I can see this is happening in this situation, this is the implication of it. The challenge of these kinds of technologies, even though they're great at perceiving the world, they're great at learning based on what's happening in the world, they tend to have very little reasoning ability, way worse than first wave technologies. And so there's been some sort of trade-off as you move from first wave to second wave in terms of the kind of capabilities. You've increased the capabilities in perceiving and learning, but you've lost the capabilities in reasoning. Many of you may have tracked the AlphaGo work that went on recently, the competition out in Korea between DeepMind's AlphaGo and one of the strongest Go players of the last decade. What's interesting about AlphaGo is that it used a combination of first wave and second wave techniques to be able to accomplish its task. I don't know how many of you are Go players, but Go is a large game. You've got 19 by 19. Every move, a stone can go on any one of the empty intersections. And so the traditional way that you might work with chess, for example, of looking at this move and that counter move and then that counter move, there are so many possibilities that you simply can't do that. What was interesting about AlphaGo is that it took the structure of how the Go stones lay out and viewed that like it was doing a sort of face recognition kind of problem. And what it had learned by looking at all thousands and thousands of professional games is, in this kind of situation, where are the potential places that a professional player is likely to play? And so it learned what are the likely good moves, and then for each of those, what are the likely good moves there? And it was able to reduce that down to a manageable kind of tree that it could then use first wave reasoning techniques to be able to find its way through. So a very fascinating way to move forward. So what we, one of the principles, I said that first wave was not good with natural data. Second wave is very well matched to natural data. And I'd like to convey to you the reason why it's well matched to natural data. There's something called the manifold hypothesis. And it sounds technical, it is technical, but we can look at it from a non-technical perspective. The manifold hypothesis says that natural data tends to form lower dimensional manifolds, whatever they are, in the embedding space. And I'm going to walk through each of the steps of this so that you get an intuitive understanding of what I'm talking about here. So first of all, a manifold, loosely speaking, is a subspace of some other space that when you move around a little bit, it doesn't really matter. You're still in the manifold. It's got a sort of neighborhood that behaves in a natural kind of way. Now, if natural data forms these manifolds, the way that I find out a picture of Bill versus a picture of Ed is that the pictures of Bill form one manifold, the pictures of Ed form another manifold, and I want to tease these apart so that I can draw a line between them. And so classification of data is done by separating these manifolds, and the way that we separate these manifolds is by transforming the space that they're in, squashing and stretching it until it's moved in such a way that you can draw a line between. And it turns out that things like neural nets and other machine learning techniques are really good at being able to construct arbitrary continuous transformations that do the transformation of the space. So I ran through that quickly. Let me go through each of those steps a little bit so that you get a stronger intuitive understanding. So let's look at this data set. This is from NIST. This is zip codes that people have written, actually the individual characters of zip codes that people have written. And each of these, in their natural representation, is a 28 by 28 pixel map. So a lot of pixels in it, but if you look at the set of zeros, you'll see that they all are kind of, in some sense, similar. It's hard for you to pin down what it means for them to be similar, but they might get slightly thicker lines, they might get slightly thinner, the loop might not quite be closed, but there's something similar about all of those zeros. And the argument is going to be that they form this manifold in the embedding space. So let's look at a particular kind of character and see what that looks like. So we've got this 28 by 28 pixels, and I always forget what 28 by 28 is, something like 764. It's a bit less than 800. So this character 8 is actually living in 800 dimensional space. That is, each of these pixel values has a value. You've got 800 data values. Now, it's hard to visualize 800 dimensional space, but the good thing is you don't actually have to visualize it geometrically. You can just say, yeah, this is a large dimensional space. Now, when I look at the individual 8s, that will be, each 8 will be one point in that space. If I look at another 8, it will be another point in that space. Another 8 will be another point in that space. And the argument is these are all kind of similar. They're grouped together with not many degrees of freedom as to how to move from one 8 to another. And I'm going to represent that by animating these 8s. On the bottom is another way of representing the 8. That's a chart of all the pixel values. So there it is, 784 things on the bottom. I just noticed it on the slide. I didn't have to do arithmetic while talking. So there's a chart of 784 values, and it's showing the pixel values of each of the pixels. Now let's animate it and run through the set of 8s. So as we run through the set of 8s, one of the things that chart doesn't change very much. Somehow we're in the same neighborhood as we go from one 8 to another 8. And that's what I'm saying. Something like the set of 8s forms a lower dimensional manifold in this vast embedding space. And it's going to be the same for all of these digits. So here's the manifold hypothesis. Natural data forms low dimensional manifolds in large dimensional embedding spaces. So the way that we separate these manifolds is by manipulating the space, transforming it, squashing it, and stretching it. So here what we have on the left is a two-dimensional space with two manifolds, the red one and the blue one. They're both one-dimensional manifolds. They're just straight lines, except they happen not to be straight in the space, but they're just lines. They're one-dimensional structures sitting in this two-dimensional space. I thought it would be easier for you to visualize one-dimensional things in two-dimensional space than eight-dimensional things in 784-dimensional space. So we'll work with this one. So let's now animate the transformation of the space. And we're going to do a linear transformation and then a non-linear, and then another linear transformation and then a non-linear, then a linear, and so on. And we get to a point by stretching this space that we can actually now draw a clean line that separates the two parts of that space. And so by continuously transforming that space using a mix of linear and nonlinear transformations, we're able to tease apart these two manifolds. And in fact, we can do that much more generally when we have multiple manifolds. We can do transformations that tease them apart such that one line, or in general hyperplane, separates off one thing, another one separates off another, a third separates off a third, and so on. Now, one of the challenges is that sometimes the manifold might be completely closed by something else. So the center of the bullseye here is one manifold, and it's completely enclosed by the rest of the image. There's no way, staying in 2 dimensions, that we can transform this image so that we can do a clean separation of the middle from the rest of it by a straight line. But what we could do is add an extra dimension, and by pushing into that extra dimension, we're now able to introduce flexibility that allows us to separate off the part that we care about, even though it was completely enclosed by something else. So the one thing that I want you to get from this set of things is that we separate these natural data manifolds by transforming the space. By doing continuous transformations, we can pull them apart. And so what we've done is now work through this complex chart and said, we go from the manifold hypothesis, which says that natural data forms these lower dimensional manifolds in the embedding space, and by step, we get to the point where we want to find continuous transformations that separate these manifolds. And so the fourth point is that computational structures like neural nets can be parameterized to approximate any continuous transformation, and so potentially at least can be parameterized to be able to approximate the continuous transformation that we care about to separate the manifolds that we care about. So let's look at how we get neural nets and structures like them to be able to compute continuous transformations. Now, here's how I describe neural nets to non-computer scientists, and I find it really helpful. Neural nets are just Excel spreadsheets on steroids. That's all they are. In fact, they're particularly simple Excel spreadsheets. What you have is you have the input data on the first sheet of the Excel spreadsheet. The next sheet does a computation based on that first sheet. The next sheet does a computation based on that. And 5 or 6 sheets later, you've got a computation where each of the things comes out naturally as the answers. So it's just layered computation as if it's an Excel spreadsheet. Indeed, we can go further. Each of the cells in the computation you could describe in Excel-style language. It's really just a sum product, if you're an Excel programmer. It's just a sum product between some set of weights, which actually we're going to have to learn. They'll start out random and we'll tune them to be the right thing. Some set of weights and the inputs to that particular cell that we care about. So that sum product is, I was talking about a linear transformation. That is the linear transformation that we use, just with different weights and choosing the input cells to it. But then there's also a nonlinear function, and I've picked the pos function here. Pos says, if your argument is positive, keep it. If it's negative, just throw it away. So it's sort of flat, and then it's the identity function in the positive space. There's other choices that you can have for the nonlinear function, but that's one that seems to be quite effective when doing learning. And so in the same way that the red and the blue lines got separated, here each layer transforms and squashes the space until we get to the final layer, and it's really easy to separate the particular faces or characters or whatever we're trying to do. Now, the neural nets is that it's these cell weights that define the transformations that are computed. The engineering of neural nets goes into figuring out how to learn those weights effectively from data. And one of the challenges, you may have heard of deep neural nets. Those are neural nets like this one, which have lots of layers. One of the challenges of deep neural nets is that as I'm working back from the answer and trying to say, how do I want to adjust the weights in order to make my answer better next time when I look at the next piece of data, as you work your way back, the initial randomness and settings of the parameters starts to get in the way as you come to the earliest values. So it's really hard to train those early values. And so what people do is add extra constraints on those early values, extra structure to get around that. So one of the techniques that they use is something called convolution. In the short version of the talk, I don't have time to explain it, but what you end up with is something like this, a multi-layered neural net where you have different computational structures imposed on early layers in order to make their learning more effective as you come back. So here you have a convolution layer, a pooling layer, then another convolution layer and a pooling layer. And you might say, why do you have all of those? And the answer is, well, maybe the person who developed this neural net started out with one convolution layer and one pooling layer, and they got up to 98% accuracy. And they said, I wonder what it would be like if I added another layer. And they tried another layer, and they got up to 99.5% accuracy. And they said, oh, cool. So this is how it works. A lot of experience, a lot of trial and error to make it. We get 99.5% accuracy. How come we failed to get 100% accuracy? Why didn't we do it all? Well, here are some of the examples that it failed on. So this one, the machine thought it was a 3, but the person had intended it to be a 5. The second one, the machine thought it was a 9, but the person thought it was a 4. The next one, the machine thought it was a 4, but the person intended it to be a 9. Or it might be the other way around, I can't remember. And that's kind of the point, right? So here's the kind of thing we use these kinds of applications for. We do a lot of processing of text and video to try and understand what's going on in particular situations. In social media, public social media, we try to find out what effect propaganda that potential adversaries might be doing have on the various people around the world. In cybersecurity, we look at how a global attack might be going on and identify the pattern of a botnet versus the pattern of some other communication sort of structure. In electromagnetics, what we do with electronic warfare is be able to construct dynamically countermeasures against the challenges that we face. We do a lot of brain-machine interfaces and understanding the neuron signals. You have to use these kinds of techniques. They're natural data, and you have to use these kinds of techniques to get through them. Now, the wonderful thing about this kind of wave is it's statistically incredible. I mean, it's truly impressive, but it's individually unreliable. Here's a couple of examples. This first one, the boy is doing a backflip on a wakeboard. I looked at that and I thought, oh, cool, I'm impressed. And then I thought, hang on, that's not a wakeboard. He's on a trampoline beside the water. And you can imagine that it's right close to the manifold of images of people doing backflips on wakeboards. And so it's a subtlety that the machine wasn't trained on, didn't understand, and so it was unable to get wrong. The bottom three examples is a risk of what we might term adversarial AI, that if somebody gets hold of your AI process, your neural net or whatever, they might be able to craft images that come out, all of these images come out with over 99% certainty that this is the image. The challenge is, in these vast high-dimensional spaces, you take a good image and you start randomly adding things which stay in the high probability, and there's room in these high-dimensional spaces to add noise. And you might say, well, who cares about this? But in the DoD, we often get very noisy, grainy pictures, and we care about being sure in sorts of situations. So it's important. Microsoft had a challenge recently when they explored a bot. And the trouble is that bot was in this dynamic environment where it responded and learned by the environment that it was in. And a set of internet trolls decided to act adversarially towards it and create an environment to lead it into a particular space that the designers never intended. And this was one of the milder comments. This was the only one I'm able to put on a slide that you get from Tay. But it shows the dangers of having this kind of learning and moving process. So that's second wave. If we want to reach beyond second wave, there's a number of applications, particularly in natural communication between humans, where you can't just have a statistical response, like if Aaron says, I'm allergic to apples, it isn't always the natural response to say, don't eat the cake. In fact, it's really a complex set of things going on to say, don't eat the cake, and a lot of these other examples. So we believe that it's important to move to a new kind of artificial intelligence technologies that we describe as third wave, and this is able to adapt to the context. And here what we believe is not that human beings will create explanatory models underlying it, but that we'll create systems that themselves build explanatory models and use those explanatory models to be able to make choices and tune themselves as they move forward. And we see that this is going to be essential to be able to get natural communication between machines and people, and not just between machines and people. The word among is carefully chosen there, among machines themselves and people and machines and so on. And we believe that these systems then will be able to learn and reason as they encounter new tasks and situations. We'll get into the space of being able to do both reasoning and perceiving and learning at the same time. And I think we'll start to get some handle on how to do abstraction, though that's still a very challenging problem, and I don't think we have any good ways forward generally. So let me give you a couple of examples of things that we're doing at DARPA, which are pushing in this kind of direction. And I only have time for 2 examples. So the first is when I get a thing back from an AI system saying, that's a cat, and I say, why do you think it's a cat? It's, well, I did my Excel spreadsheet calculations, and cat came out as the highest number. That's not a satisfactory explanation. What we want is something underneath which says, well, it has these kinds of features, these kinds of characteristics. That's why I think it's a cat. And I think it's really important for us to be able to take a lot of our classification systems and other systems and move into this kind of direction. Another thing, this work is related to one of our projects on probabilistic programming, but was done outside of this work. It's one-shot learning. In this particular situation, you write a model, this was handwritten in this case, you write a probabilistic model for how the hand writes strokes. Like if you're writing things, here's one stroke, here's another, how does the hand move? You then give it one example of a character, and this is a made-up alphabet. Give it one example of the character. The machine tunes that to the model and says, oh, I get that the character is made up of those strokes. And on one example, it becomes as good as a neural net trained on tens of thousands of examples at being able to recognize characters in that. So I'd like to just close in my final couple of minutes saying that AI, progress in AI, comes from sustained investment. Bill made that point in the introductory comment. There's been a lot of federal funding from very many agencies over the years pushing this forward, and it gets to the point at which we are able then to bring it to the commercial world, industrial world, the defense ecosystem and so on, being able to apply these things in practice. But just in natural language processing, many things that DARPA itself has been involved in that have led to things like Siri on your phone, or it's led to the application of real-time translation, say from Arabic into English and things like that. So I'll close just with a bit of an eye chart. I said that there are 3 waves of AI. Just because it's first wave doesn't mean that it's old and boring. We're still doing stuff in first wave. We're imagining new things that we're doing in first wave, but it's also key for us to be investing in second wave and in third wave as we move forwards. And with that, I'll close. Thank you very much.